This is section 2.4. We're going to be talking about symmetry of graphs and functions. Alright, so we're going to say that a graph has symmetry with respect to the x-axis if the x-axis serves as a mirror image. So what's above the x-axis is reflected on the x-axis with what's below the x-axis. So for instance, here we have on the left over here an example of a graph that's symmetric with respect to the x-axis. The thing to notice is that, let me imagine that I pick a point on my graph, let's say this point right here. It's got coordinates x and y, let's just say. And so then the thing you need to notice is that since this graph is symmetric with respect to the x-axis, this point right here, if you kind of just go vertically down and across the x-axis, well, then it should have its partner value over here, whose coordinates should be the same x value. It's just that the y coordinate is now negative. So this is negative y. So if you have x comma y, then we're going to have x comma negative y. So I hope you see that. So here, for instance, I have the point x comma y right there. Well, I have the corresponding point x comma negative y. And that's because this graph is symmetric with respect to the y-axis. Sorry, the x-axis. But notice that this is not a function. This is not a function. It fails the vertical line test. That's okay. Sometimes our graphs are not functions, so that's no problem. We can have symmetry with respect to the x-axis. It's just that if a graph is symmetric with respect to the x-axis, it is not a function. Okay, now we can also have symmetry with respect to the y-axis. So in the y-axis, I don't know, imagine that I pick a point, any point on my graph, and let's assume that the graph is symmetric with respect to the y-axis. So let me pick this point instead. There we go. So right there, I'm gonna pretend that it has coordinates x comma y. Well, in this case, I guess it would be negative x comma y. Well, since it's symmetric with respect to the y-axis, I should also have the point x comma y. Yeah, and so then if you have the point x comma y, then you should also have negative x comma y included in your graph. That's if the graph is symmetric with respect to the y-axis. Now, symmetry with respect to the origin. Symmetry with respect to the origin is a little bit more kind of, I don't know, the way I understand it is like this. Imagine that you put a little pin right at the origin. Imagine that you can put a nail right at the origin, and that your graph is movable, and imagine that you rotate the graph 180 degrees. So you put a little nail right at the origin, you rotate your graph either counterclockwise or clockwise, it doesn't matter, 180 degrees, and then you have to ask yourself, does it land back on itself? If it does, then you have symmetry with respect to the origin. Yeah, that's maybe one way to maybe think about it. Imagine putting a little nail right at the origin and you rotate your graph 180 degrees. Does it land back on itself? If it does, you have symmetry with respect to the origin. Here what happens is that if you have the point x comma y, well, then you should also have the point negative x comma negative y. So if you have the point x comma y, you should also have the point negative x comma negative y. Yeah. So let's see. So that's it's easy to determine symmetry if you are given a graph. If you're given the graph, you just look at the graph and you say, oh, it's symmetric with respect to the y-axis or the x-axis or the origin or whatever it may be. It gets a little bit trickier if you're not given the graph. If instead you're just given an equation, if you're just given an equation and you are asked, is the graph of this equation symmetric with respect to the whatever axis? Or then that's a little bit trickier to determine. And so then here we have some rules. So if you're given an equation, if you just are given an equation with x's and y's, if you want to determine if the graph of that equation is symmetric with respect to the x-axis, if you replace y with negative y and you end up with the equivalent equation, then the graph of your equation is going to be symmetric with respect to the x-axis. If, let's say you're testing for symmetry with respect to the y-axis, if you replace your x's with negative x and you end up with an equivalent equation, then the graph is symmetric with respect to the y-axis. And in order to test to see if your graph is symmetric with respect to the origin, if you replace your x with negative x and your y with negative y, and you end up with an equivalent equation, then the graph is symmetric with respect to the origin. Yeah? Okay, so let's see. Again, it's easy to answer these questions about symmetry if you have the graph. But here in the next example, in a couple of examples here, we're going to get into a situation where all we have to work with are equations. That's where we're going to have to refer back to these little rules here, these little tests. Okay, but before we get into that, let's just do a simpler exercise here. So we were given the point negative 5,6. Let me plot it. Let me put it in the, so negative 5,6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That's my point, negative 5,6. Yeah? It's negative 5. And that's 6. Let me just double count. 1, 2, 3, 4, 5, 6. Good. So that's my original point. Now they want us to give a point that's that would be symmetric with respect to the x-axis, the y-axis, and the origin. So pause the video, see if you can find. So you're supposed to come up with 3 points here. One point that's symmetric to this point that was given to us, but it's symmetric with respect to the x-axis. The other point should be symmetric with respect to the y-axis, and the other point should be symmetric with respect to the origin. Alright, so hopefully you try this. You already have your coordinates for the other points. Let's see, I'll do them in different colors. So let's first take care of this. I want to find a point that's symmetric to this one, and it's symmetric with respect to the x-axis. So I'm looking at the x-axis, it's right here. This is my horizontal axis. And if I'm looking for a point that's symmetric to this one with respect to the x-axis, that just means it should be down here in the third quadrant. Yeah? And it's going to have the same x-coordinate. It's going to have the same x-coordinate. It's just that my y-coordinate is going to be negative. I guess in this case it's going to be negative 6. So negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. Okay. So I think we're dealing with that point right there. Yeah? I think we're dealing with this point right here. That would be negative 6. So then the coordinates here should be negative 5, same x, but negative y coordinate. Negative 5, comma negative 6. Okay, let's use green for symmetry with respect to the y-axis. Okay, so this is my original point, negative 5, comma 6, and I'm looking for a point that's across from the y-axis, so that it's symmetric with respect to the y-axis. So then that means that the y-coordinate is going to stay the same. What's going to change is the x-coordinate. Instead of being negative 5, it should be positive 5 now. So let me count. 1, 2, 3, 4, 5. So that's 5 right there. 1, 2, 3, 4, 5. So that's 5. And I'm going to draw this guy in red. Sorry, in green. So that is my new point. So that point is 5, comma 6. Yeah. Let's compare that to like the original one. The original one was negative 5, comma 6. This guy's just, I changed the x coordinate to positive. It's still the same y coordinate. Okay. So let's think of a point that's symmetric with respect to the origin. Okay, I guess before we come up with the point, in which quadrant should the point that's, so this is my original point, negative 5,6. I'm looking for a point that is symmetric with respect to the origin to this one. And so then in which quadrant should it lie? Hopefully you agree that it should lie in quadrant 4 over here. So we're going to have to be opposite of each other. So to come up with this point, or I'm going to have to change both coordinates. So in this case it's going to become, let me try, I don't know, what other color can I try here? I guess blue. That's my other choice. So here the coordinates are going to become, you have to change the sign of the x and the y. So this becomes negative 5, sorry, not negative 5, positive 5, comma, negative 6. So 5, comma, negative 6, that's right there. All right, so hopefully we agree on these points and this idea of symmetry for a graph. Just remember that if a graph is symmetric with respect to the x-axis, it's not a function. It's not a function. That's okay. It's still just the graph of some equation, but turns out it's just not a function. All right, so let's try the next exercises then. These are a little trickier. So we have these 4 little equations. We do not know what the graphs of them look like. Well, maybe you do. I don't know, maybe you do. If you do this, then answering this question becomes a little bit easier. But if you do not know what the graph looks like, then we're going to have to think of our little algebraic rules to determine symmetry. Okay, so I want to test for symmetry with respect to the x-axis, y-axis, and the origin. Yeah, I want to know if what's going on. I mean, I guess it could also be the case that we do not have any type of symmetry. There's no symmetry with respect to the x-axis, there's no symmetry with respect to the y-axis, and there is no symmetry with respect to the origin, in which case we'll say there is no symmetry. I'll help you with the first one. And then you'll do the other ones. So let's see, let's think of, I'm gonna test, so I'm gonna test for symmetry with respect to the y-axis first. So I'm testing for symmetry with respect to the y-axis. How do I test for symmetry with respect to the y-axis? Let me go back up here. So if I am testing for symmetry with respect to the y-axis, if I replace my x's with negative x and I get the same equation, then I have symmetry with respect to the y-axis. Alright, so let's see. So then that means replace x with negative x. So let's see. So let me look at my equation. So I would have y equals, I'm going to replace my x's with negative x. So I have to be careful. I'm going to put a parenthesis about it. So negative x squared plus 2. See, what I did is I replaced my x with negative x. But I have to be careful because there's a big difference between negative x squared and negative x squared. You see, these two little things are very different scenarios here. So you gotta be careful with parentheses and thinking about what it means to plug in something into an equation. So my x got replaced with negative x, but I had to put a parenthesis around that because then it's being squared. Alright, so good, I replaced my x with negative x, and now negative x to the second power, a negative times a negative becomes positive. So this then just becomes pretty much, it becomes identical to the original equation that we started with. So this is symmetric. This equation, turns out that the graph of this equation is symmetric with respect to the y-axis. So the graph of this little equation is symmetric with respect to the y-axis. I'm going to test symmetry for the other cases, just to show you how to go about it. So let me test for symmetry with respect to, now the x-axis. So here I would have to replace would have to replace my y with negative y. So then that would look like this. Negative y equals x squared plus 2. And well, there's really not much more to do here. Just negative y equals x squared plus 2. Does this look like the original one? I would say no. It doesn't kind of look like the original one. So it's not symmetric with respect to the... So this is not symmetric with respect to the x-axis. So we'll say no. Lastly, let's test for symmetry with respect to the origin. So now what we have to do is replace x with negative x and y with negative y. So let's do that. So that looks like this. Negative y equals negative x squared plus 2. Yeah? And if I simplify this just a little bit further, I end up with the following. Negative y equals positive x squared plus 2. And well, this equation that we got out from replacing x with negative x and y with negative y does not look like the original one. So that means that the graph of my original equation is not symmetric with respect to the origin. So we do not have symmetry with respect to the origin in this case either. So we do not have symmetry with respect to the origin in this case. The only type of symmetry that we had was symmetry with respect to the y-axis. And that's how, so that's what you have to do for this other 3 exercises. You gotta check what type of symmetry does your function have. Sorry, does your equation have? Because we do not know if these things are functions. They might not be functions. If they were functions, we might be just using function notation, f of x, g of x. But we do not know at this moment. Okay, so pause the video, take a few minutes, and determine what types of symmetry do the other equations have. Okay, so hopefully you've tried this and you've determined what type of symmetry we're dealing with here. So I'm going to kind of do my tests for symmetry. I'm going to begin by testing around the y-axis. So y-axis symmetry. Okay, so in order to test for symmetry about the y-axis, what we said is we replace our x's with negative x. So then that looks like this. 2 times negative x minus 5 equals 3y. Let me kind of simplify this a little bit. Well, this is just negative 2x minus 5 equals 3y. Is this equation equivalent to the original one? I would say no. This guy up here had the positive 2x. Now this guy has negative 2x. So is my equation, is the graph of my equation symmetric with respect to the y-axis? I would say no. Let me test for symmetry with respect to the x-axis. In order to test for symmetry with respect to the x-axis, I change my y's to negative y. Okay, so then my equation looks like this. 2x minus 5 equals 3 times negative y. Okay, let me simplify this a little bit. And that is what I have. Is this equation equivalent to the original one? I would say no. I mean, there's definitely the difference being the negative 3y and the 3y. So it looks to me as though this function is also not symmetric with respect to the to the x-axis either. So the graph of this thing is not symmetric with respect to the x-axis. Let me test for symmetry about the origin. Okay, so that means change my x's to negative x. So that would look like this: 2 times negative x minus 5 equals 3 times negative y. And then let me kind of clean this up, simplify this. That's negative 2x minus 5 equals negative 3y. Is this equation equivalent to the original one? I'm going to say no. I mean, even if I was to multiply both sides by negative 1, I would end up with a different equation altogether. So I guess what I can conclude is that, yeah, this equation is not equivalent to the original one. So turns out that this equation, the equation for B, doesn't have any type of symmetry. I mean, it's a graph. It's some line, but it doesn't have symmetry with respect to the y-axis, the x-axis, or the origin. That's okay. If anything, probably turns out that probably most functions are not symmetric. Most graphs are not symmetric with respect to anything. So that's okay. So this one has no symmetry. Part B has no symmetry with any axis or the origin. Let's do C. Let me test for symmetry with respect to the y-axis. To test for symmetry with respect to the y-axis, I replace my x's with negative x. Okay? So I replace my x with negative x. And well, now here it kind of gets a little tricky. This negative in the denominator, I could move it to the top, or I could just put it in front of my fraction. And if I was to put it in front of my fraction, what ends up happening is that it becomes negative, negative, which makes the thing positive. So this is the simplified form of this. It's just positive 4 over x. So I am going to go ahead and conclude that this has no symmetry with respect to the y-axis. Why? Because this equation, the simplified form, I replaced my x's with negative x, I simplified, and it's not equivalent to the original equation. So this equation is not symmetric with respect to the y-axis. What about the x-axis? Alright, in order to check for symmetry with respect to the x-axis, we change y's to negative y. So negative y equals negative 4 over x. Is this equivalent to the original one? I mean, if you wanted to here, you could multiply both sides by negative 1, and this would become positive, and this would become positive, but even then, it's not equivalent to the original one, because the original one part was positive, the other one was negative. So, turns out that, yeah, this is not equivalent to the original one, so there is no symmetry with respect to the x-axis. Let me test for symmetry with respect to the origin. Okay, so in order to test for symmetry with respect to the origin, I change my y's to negative y, and I change my x's to negative x. Here it gets a little tricky. Here it definitely helps for you to know and be comfortable with rules, with signs. When is something positive? When is something negative? So let's see. Is this expression right here, negative y equals negative 4 over negative x, equivalent to the original? Let's see. Is it? One thing we could do is the following. Well, if you notice on the right hand side here, I have this negative and a negative in the denominator. So that makes the right hand side actually positive. It's like saying negative 1/3. Yeah, something like that. So then this becomes negative y over, now the right hand side becomes positive. Why? Because of this negative negative situation that we have. So that's just 4 over x. Yeah. And now think about this equation. Is this equation equivalent to the original one? Turns out it is. Turns out it is. Why? Because I could multiply both sides of this equation by negative 1. So I'm going to multiply both sides by negative 1. And if I do that, then I end up with y equals negative 4 over x. Yeah, and that is exactly the same as what I started with. And so I don't know if that's good or bad, I don't know. But what that tells me is that I have symmetry with respect to the origin. So it turns out that the graph of this equation, whatever the graph looks like, is symmetric with respect to the origin. Just be careful here. Sometimes you have to play and manipulate. So you change the x's to negative x, you change the y to negative y, and then you might have to then be careful with your rules for signs. Okay, so the graph of this equation, is symmetric with respect to the origin. Let's try the last one. Let me check for symmetry with respect to the x-axis. Okay, so I'm gonna check for symmetry with respect to the x-axis. That means that I gotta change my y's. Or actually, let me begin. I began all of. Let me first check for symmetry with respect to the y-axis, just to be consistent. And in all of the other exercises, I first began by checking symmetry with respect to the y-axis, and then the x, and then the origin. So y-axis. So in order to test for symmetry with respect to the y-axis, I change my x's to negative x. So that looks like this then. 2y squared is equal to 5 negative x squared plus 12. Yeah, so I change my x to negative x. I just gotta be careful that I put a parenthesis about my negative, because then it's gonna get squared. Okay, so then I need to simplify this. A negative squared becomes positive, so negative x times negative x just becomes x squared. So then this is 5x squared plus 12, and I'm going to say, well, this new equation that I got after replacing my x's with negative x is identical to the original. So I'm going to conclude that the graph of this equation has symmetry with respect to the y-axis. That's good, I guess. I don't know. Let me test for symmetry with respect to the x-axis. In order to test for symmetry with respect to the x-axis, I change my y's to negative y. Okay. And that's what it looks like once I change y to negative y. So I have 2 times negative y squared equals 5. Okay. And then I gotta simplify this a little bit. And again, I gotta square negative y. So negative y times negative y, well, that's going to become positive y squared. So this simplifies to 2y squared equals 5x squared plus 12. And I'm looking at my simplified, so I replace my y's with negative y, and I ended up with the exact same equation as the original one. So this has symmetry with respect to the x-axis. If something has symmetry with respect to the x-axis, it should automatically tell you that it's not a function. So this thing is not a function. It's very symmetric, but it's not a function. Lastly, let me test for symmetry with respect to the origin. Okay, so I gotta replace my x with negative x, my y with negative y. Well, that becomes 2 negative y squared equals 5 times negative x squared plus 12. And then let me simplify this. Well, this simplifies just to 2y squared equals 5x squared plus 12. And remember, the reason why this is because negative y squared becomes positive y squared. So negative y times negative y is positive y squared. Okay, and the simplified form that I get after replacing x with negative x and y with negative y looks identical to the original equation I started with. So then that means that this has symmetry with respect to the origin as well. It's a very symmetric graph. This has symmetry with respect to everything. Y-axis, x-axis, and the origin. What type of graph are we dealing with here? What is the graph of this thing? Turns out that this is a circle. This is a little circle. It's probably, I do not know where it centers, but it's a circle. And if you think about a circle, yeah, well, a circle is very symmetric. Okay, so hopefully this so if you're just given an equation and you're asked about the symmetry of the graph, now you know how to proceed. If you're testing for symmetry with respect to the x-axis, you replace y with negative y. If you are testing for symmetry with respect to the y-axis, you replace x with negative x. And if you are testing for symmetry with respect to the origin, you replace x with negative x and y with negative y. Okay, let's move on. Now let's talk about functions. Let's talk about functions. So remember, if you have symmetry with respect to the origin, that means that it's not, if you have symmetry with respect to the x-axis, it's not a function. It is not a function. So functions can only be symmetric with respect to the y-axis and with respect to the origin. So an even function is a function that's symmetric with respect to the y-axis. An odd function is a function that's symmetric with respect to the origin. So even functions, even is symmetric with respect to y-axis. Odd, then you're dealing with symmetric with respect to origin. Okay, so even functions are symmetric with respect to the y-axis, odd functions are symmetric with respect to the origin. Now we're going to be using function notation, f of x, g of x. So to algebraically test to see if a function is symmetric with respect to the y-axis, you're going to change your x to negative x. Kind of the same thing as what we did earlier when we were trying to test for symmetry with respect to the y-axis. You change your x's with negative x. That's why here we have this little rule that says f of x equals f of negative x. To test to see if your function is odd, you are going to do this little test which says that f of negative x should equal negative f of x. Yeah, this is equivalent to changing x to negative x and y to negative y. Okay, so we'll use this here in a bit, but let's just begin with something a little bit easier. So we gotta determine which functions are even, odd, or neither. And right now the question is not too difficult because we are given the graphs. So remember, an even function means that you have symmetry with respect to the y-axis. An odd function means that you have symmetry with respect to the origin. So pause the video. There's these 6 little graphs. Determine the types of symmetry that these graphs have. And all of them are functions. All of them happen to be functions. Okay, so hopefully now you have determined which ones are even, which ones are odd. So let me look at the first one here. Is this even or odd? So if I want to know if it's even, I gotta ask myself, is there symmetry with respect to the y-axis? And I would say no. If I want to know if this function is odd, I want to ask myself, is there symmetry with respect to the origin? And remember, symmetry with respect to the origin means imagine putting a little nail right at the origin, rotate your graph 180 degrees. Does it land back on itself? I don't think this one does. So for the first one, I'm going to conclude that this is a neither. What about the second one? I would say that the second one is symmetric with respect to the y-axis. The y-axis splits my little graph right in half. So then that means that it has symmetry with respect to the y-axis, or that it's even. So this one is even. What about this third one here? It's not symmetric with respect to the y-axis, but if you were to put a little pin right at the origin, put a nail in the origin, imagine that your graph is movable and you rotate your graph 180 degrees. Does it land back on itself? I would say yes. So this is an odd function. What about this one? Graph 4. Is the graph 4 even or odd? It's definitely not symmetric with respect to the y-axis. But if I put a little pin right at the origin and rotate my graph 180 degrees, either counterclockwise or clockwise, it doesn't matter. You could rotate counterclockwise or you could rotate clockwise, it does not matter. Rotate 180 degrees, does it land back on itself? I'd say yes. This graph does land back on itself. So this is going to be odd. This graph right here, even or odd? What do you think? If I rotate this about the origin, or well, it's definitely not symmetric with respect to the y-axis. There is no symmetry with respect to the y-axis. So that's okay. I can see that kind of easily. What about symmetry with respect to the origin? If I put a pin at the origin and rotate the graph 180 degrees, does it land back on itself? And I would say no. I would say that this does not land back on itself. This is neither. And lastly, graph 6. I would say that that's symmetric with respect to the y-axis, so even. Okay, I think that's what we're dealing with here with these little graphs. Now, the question will be, now we do not have the graph available to us, and we want to determine if the function is even, odd, or neither. Okay, let's see. I'll give you the opportunity to try them on your own. You're going to have to think about this. You're going to have to think, you have to do this test for even. You're going to have to see if f of x equals f of negative x. Or you're going to have to see if f of negative x equals negative f of x. Yeah, to determine if it's odd. Or if neither of these situations happen, then it's neither. So pause the video and see if you can determine if these functions are even, odd, or neither. Alright, so hopefully now you know if they're even, odd, or neither. Let's just compare answers. So I'm going to do part A. I want to determine if this little function is even, odd, or neither. So in order to do that, I'm going to compute a few things. I'm going to compute this thing first, f of negative x. I'll figure out what it is here in a second. I'm also going to compute negative f of x. And then I'm going to do some comparisons. Alright, f of negative x. That means I have to change my x to negative x. So that becomes 5 negative x to the 7th minus 6 negative x to the 3rd minus 2 times negative x. Okay, let me just give myself a little bit of room here. So f of negative x means replace all your x's with negative x, and that's what I've done. Notice that I put my negative x's in parentheses because they're being exponentiated or they're being multiplied by something else. So now I gotta be careful with signs. A negative number raised to an odd power is going to be negative. A negative raised to an odd is always negative, because imagine like negative 1 times negative 1 times negative 1, well that's negative 1. A negative raised to an even power, that's when it becomes positive. Okay, so then this becomes negative 5x to the 7th. Now here, see, negative x to the 3rd is going to be negative x cubed, but then you multiply a negative x cubed times negative 6, and that becomes positive. So plus 6x to the 3rd, and then plus 2x. So be careful with, so hopefully here there is, you're okay on what I did here. So the negative x to the 7th, well that becomes just negative x to the 7th. Negative x to the 7th times positive 5 becomes negative 5x to the 7th. And then negative x to the 3rd power, that becomes negative x cubed. Negative x cubed times negative 6 becomes positive 6x cubed. And then negative 2 times negative x is positive 2x. So that is f of negative x. Let me also compute this thing. Negative f of x. Okay, negative f of x just means put a negative in front of your original function. So it looks something like this, and then I have to distribute the negative. So that's negative 5x to the 7th plus 6x to the 3rd plus 2x. Okay, so this is just the groundwork. This is just the groundwork. Now let me actually think about the tests. So my function is even. My function is even if f of x equals f of negative x. So is that true for us right now? So I'm looking at f of x. This is the, so look, f of x, that's what we were given up here. So f of x is supposed to be equal to f of negative x. That's when our function is even. Okay, so is that the case for us right now? So I'm looking at f of x. This is what it looks like. And then f of negative x is negative 5x to the 7th plus 6x to the 3rd plus 2x. Are those two expressions equal? And I would say no. So in our case, this is no. So this is not an even function. It's not an even function. So hopefully, yeah. So right now, this function is not even. Let me test for odd. So my function is going to be odd if f of negative x equals negative f of x. So now I'm comparing this f of negative x to negative f of x. Is this equation equal to, or is this expression equal to this one? Well, let's see, f of negative x was negative 5x to the 7th plus 6x cubed plus 2x. Is that equal to negative 5x to the 7th plus 6x cubed plus 2x? Yes. This is, it looks to me like this is odd. Yeah, so that's what I have to do to test if a function is even or odd. I have to compute f of negative x and I have to compute negative f of x. And then I have to do some comparisons. So this function is odd. This function in part A is odd. It has symmetry with respect to the origin. Alright, let's see. Let's try the last one. I have to compute h of negative x. which is going to be 5 negative x to the 6th minus 3 negative x to the 2nd minus 7. Okay, now I have a negative raised to an even power, so that becomes positive. So that's 5x to the 6th. And then here, look, be careful with this, the signs. Negative x squared, that's going to become positive, but then you're going to multiply by a negative 3. So that's going to be negative 3x squared minus 7. That's h of negative x. Let me compute negative h of x. Okay, negative h of x is just a negative and then our original function. Okay, so that becomes negative 5x to the 6th plus 3x squared plus 7. Okay, right now that's just the groundwork that I need in order to make now my comparisons. So now let me think, is this function even? To be even, that means that f of x equals f of negative x. So that means, is the original equal to h of negative x? I guess let me change things to h here, just to kind of use the same notation that we were given here, h. Is h of x, is the original one equal to h of negative x? So 5x to the 6 minus 3x squared minus 7, that is equal to 5x to the 6 minus 3x squared minus 7. So this looks even. Yeah, this is an even function. This is an even function. Why can't I change colors quickly? Sorry, my computer. So this is even. Is it odd? Could you have a function that's both even and odd? So to be odd, that means that h of negative x should be equal to negative h of x. Well, let's see. Here's h of negative x, we computed it, that's 5x to the 6 minus 3x squared minus 7. Is that equal to negative 5x to the 6 plus 3x squared plus 7? No. So this thing is not odd. This is not it's not an odd function. It's an even function. Yeah. So this is how we determine if a function is even or odd. We have to make there's a little bit of groundwork that you first have to do. You have to compute this thing called h of negative x, and you have to compute negative h of x. You gotta simplify these forms and then do your comparisons. Okay, well, that is it for this section. I guess I leave you with the question: is there a function? It has to be a function, so it has to pass the vertical line test. Is there a function that's both even and odd? All right, thank you, and I'll see you in the next video.